In this video, we're going to continue our discussion with completing the square. Let's make a quick note then. To solve a quadratic equation using completing the square, the leading coefficient must be 1. To solve an equation by completing the square that is in the form of ax squared plus bx plus c equal to 0, divide both sides by a to make the leading coefficient 1, have it in the form of, and set that equal to 0. Complete the square. Whatever is added inside the parentheses should be subtracted outside the parentheses on the same side of the equation. This ensures that the equation is balanced. Factor the trinomial to a perfect square trinomial and use the square root property to solve the equation. All right, so let's solve each equation by completing the square. Notice the leading coefficient is 1, so I don't need to divide anything out. So let's write it out in the form. So I'm going to take half of -4 and square it. That's 4. So I'll be adding 4 on the inside and subtracting 4 on the outside. Well, the trinomial factors as x minus 2 squared, and 6 minus 4 is 2. Subtract the 2. And now take the square root of both sides. Remember, that's plus or minus. The square root of -2 can be rewritten as the square root of 2 times I. Again, make sure the I is outside the square root. And add 2. So my two solutions are 2 plus the square root of 2 times I, and 2 minus the square root of 2 times I. Okay, let's do the next example. Now again, notice the leading coefficient is a 1, so I don't need to divide anything out. So let's write it in the form. All right, so let's complete the square. Half of 7, that's 7 halves. And 7 halves squared is 49/4. So I'm going to add 49/4, and I'm going to subtract 49/4. Now remember, I'm going to use the first part of the completing the square part in order to help me factor. Because it's positive 7 halves, I can factor it as k plus 7 halves, a quantity squared. -1 minus 49/4. I've done on the side, that's -53/4. Add the 53/4. Take the square root of both sides. Now, that square root of 4 on the bottom, that simplifies to 2. There are no perfect roots I can pull out of 53 other than 1. So I'm going to subtract these 7 halves. And because I have the same denominator, I'm going to rewrite it. Okay, let's take a look at the next example. Notice here the leading coefficient is a 2, so I must divide every single term by 2 first. Let's write it of the form. So let's complete the square on the side. Half of 2 is 1, and 1 squared is 1. So add 1 and subtract 1. So w squared plus 2w plus 1, that factors to be w plus 1 squared. 3 halves minus 1, that's the same thing as 3 halves minus 2 over 2. That's a positive 1 half. Subtract the 1 half. Take the square root of both sides. Again, plus or minus. Now, let's simplify the square root of negative 1 half. When I do that, that's the same thing as the square root of 2 divided by 2 times I. And then subtract 1. And there are my two solutions. I'm not going to try to find a least common denominator. I'm going to leave my answer like this. All right, so let's take a look at the next example. Again, notice the leading coefficient is a 3. In order for me to complete the square, I must divide every single term by 3 first. All right, so let's write it in the form. Now, let's complete the square. So half of negative 10 thirds, that's negative 10 over 6. That's negative 5 thirds. Take that and square it. That's 25 ninths. So I'm going to add 25 ninths, and I'm going to subtract 25 ninths. Now remember, I'm going to factor this trinomial with the help of the first part of completing the square. That's negative 5 thirds. So I can factor it as p minus 5 thirds squared. Now, let's do negative 4 minus 25 ninths. And that's negative 61 ninths. Add the fraction. Take the square root of both sides. Again, don't forget it's plus or minus. That square root of 9 in the denominator, that simplifies to 3. And there's no perfect roots I can pull out of 61 other than 1. Add the 5 thirds. Because the denominators are the same, I'm going to write it as 1 fraction. And here are my two solutions here.